Now we are going to visualize what it means to have a current in a circuit, in a loop circuit, in a closed circuit. Imagine that you have a closed circuit like this. The first observation is a constant electrical field cannot maintain a current. Why? Because even it's not a constant too. An electrical field E that depends on R cannot maintain a current, cannot maintain a continuous current, a current. Why? Because imagine that you have an electrical field E. E may be depend on the position R. Maybe E depends on the point where you are. E, the circulation of E scalar DDR, what does it mean? The sum of all the E for all the DDRI through the closed circuit. So it will be something like this. The value of E, whatever it is, by the value of DDRI. In this case, you see the DRI, this is almost, the dot product would be almost zero. But here, the value of E by the DDRI will be negative, because the projection will be negative, the dot product, and the things is that E DDRI here will be positive, but the sum will be zero, because it's a conservative field. If EDR is conservative, the circulation of E scalar DDR over a closed path will be zero. But this is V sub E, this is the charge, the energy per unit of charge. This is energy per unit of charge. This is the V sub E, but V sub E is zero, so there is no current. The current would be zero. There is no way to maintain the current, because the charges here, dDq, will be flowing with certain velocity, but at some moments, the energy that they will gain, they will lose in some path, in some part of the path, and he will arrive here with no energy. So they increase the energy, they increase the energy, they decrease the energy, they decrease the energy, they decrease the energy because the dot product is negative, and so on, and at the end, the total energy per unit of charge will be zero. So there is no electromotive force. V sub E in a circuit is what we call the integral of E scalar DDR. Oh, there is now an E that has no exactly origin on electrical field. It has the origin of something that is a chemical reaction. So we have a battery, and we say that the battery gives energy per unit of charge to all the charges that are passing through here. So you pass the charge dDq from here to here, and you give the energy V sub E to every charge and per unit of charge. And what is the total energy? The total energy would be V sub E by dDq, by the energy per unit of charge. By the charge is the energy that you give them. So the battery is creating an energy that gives to the to the moving charges, gives energy to make possible that they will come back in a closed circuit. Here is the electrical field E, that is, you see, this charge will have to climb, this electrical field is going in the contrary direction that it should go, because the positive charge, if the electrical field is like this, the force will go like this, Q by E. So there is a chemical reaction that makes a force that will be exactly equal to this force, Q by E, and this is a non-conservative force. That's why the integral of E scalar ddl is different than zero, because the force implies it's not conservative. So you climb because the battery give energy per unit of charge to every charge, and you create a current. How you visualize this in a let's go to see what is happening here. How you visualize the current moving? I know. You imagine a continuous current. This is the battery. This is like a pump. It's pumping charge. It's taking charge, and you imagine a movie that is continuous. This charge is moving, and now the following charge is moving and is occupying this position. This charge is moving, and in the time t, they will go here with more energy, and is moving with constant velocity v. This charge is moving with constant velocity v, v sub d, draft velocity. So the charge is moving, and you have to imagine that the whole cable have a resistance. Normally, you concentrate the resistance in some part of the cable, and you say here is the resistance, but the resistance is from the beginning, from the point A to the point V, following this path. But you concentrate the resistance here. And what the equation that you write for all the circuit that you will have is that energy gain from going to A to V is energy lost, and the energy loss is R by I, or V sub E, energy gain from here to here, from the negative to the positive pole of the battery, minus R by I equals 0. And this is the equation that you use all over the circuit. So when you see a circuit, you see a flow of charge. How you see the flow of charge? Let's say that this is the battery here, this is the battery here, and this is the cable here. And imagine there is like a cloud of charge, many clouds of charge, okay, many cloud of charge. So the battery take one cloud of charge, put it here at a higher potential, so it's like gravitational potential is a higher potential, so now he can fall from the higher potential, positive, to the lower potential, and the cloud that is here, the cloud of electron, is moving through the cable. So this is the cable, okay, this is the cable. So the charge is moving because there is an electrical field here, E, that is moving the cloud of charge. But the distance that they are moving, they are very, very small distance. In the time delta t, maybe the velocity v sub d of these clouds, if you calculate, is around 1 millimeters per second, or maybe less than 1 millimeter per second, I don't remember, but it moves very, very slowly. And you can find this from this equation. J by the area, that is the current, is NQ V sub D by the area. So you place numbers, let's say N, the number of charge per unit of volume, let's say 10 a la 20 moving particles per volume, 10 a la 20 per meter cubed. You plug in numbers, electrons, you imagine electrons, 1.6 by 10 a la minus 19. You imagine a current of 1 ampere and try to find V sub D. Okay, what will be V sub D? And imagine the cable has an area, let's say the area, I don't know, area corresponding to a radius of 1 centimeters. So make this exercise and find V sub D for this case. And you will find that V sub D is very small. So the image is like a water flowing through a cable in a continuous way. So, but instead of water, they are electrons. They are cloud of electrons that are being pushing by the electrical field, but they don't gain. They are not totally accelerating. They are having collision with the lattice. So at the end, the collision is acting like a friction force, and at the end, all the clouds, they are moving with constant velocity V sub D. So this is the image that you have to see, a continuous flow of water, like a river where the water or never change. It's a stationary things what you see that every point is moving with velocity V sub D, every charge is moving with velocity V sub D, so the current is constant, and the current is maintained because there is a pump here. There is a battery with charge V sub B, and the battery give energy V sub B and per unit of charge, and the charge lose the energy R by I in giving it's not one circle, it's not one round, it's moving a little bit. When they do like this one will do like this. It's not that you need, the charge has to flow one round. No need to do it. So this is current, charge per unit of time. Okay, that is flowing here through the surface. Charge per unit of time that is flowing equals 0. So the energy per unit of charge that you give is losing, and the amount that he loses is R by I. That's all.